All right, good afternoon, everybody. We're going to begin our afternoon session. It is 1 o'clock, so if you'd like to come back in and find your seat. We're going to begin the afternoon with presentations on fracking and water contaminants. Our speakers today are Dr. Susan Brantley, Barnes Professor of Geosciences and Pugh University Professor, Department of Geosciences, Earth and Environmental Systems Institute at Penn State University, and Dr. Jennifer Baka, Associate Professor of Geology, Associate Faculty in Institutes of Energy and the Environment at Penn State University. So please welcome Dr. Brantley.
Hi, actually, Jen, this is Jen Baka. I'm going to go first, followed by Sue, and I will be running the slides. So can you see the slides in the room?
Yes, we can see them.
Great, thank you. Well, it's a pleasure to be here this afternoon. I'm going to present an overview of some work that Sue and I have been working on to understand the linkages between unconventional energy development, water contamination, and public health down in southwestern Pennsylvania and Beaver, Washington, and Greene counties. So the objective of this study, which we've been conducting for the last 2 years, was to study this energy water health nexus in those 3 counties. And what we did was integrate social science research that I led and geoscientific analysis of a water sampling database. And what I'm going to present first is that social science analysis, which is based on community focus groups that we've been doing for the last 2 years. I'll review those findings with you and then turn it over to Sue, who will review the geoscientific analysis that her group led. All right, so what we did for these focus groups, we held sessions in Beaver, Washington, and Greene counties in the summers of 2022 and 2023, one each in each of those 3 counties for a total of 6. The sessions lasted 90 to 150 minutes. And for the focus groups that we did this past summer, we did them again with the same people who attended the 2022 sessions because we wanted to share our preliminary results with those communities and review our interpretations of the data with them to make sure that we were on the right track. All these sessions were recorded and transcribed using qualitative analysis software, and we didn't go into that data set looking for specific hypotheses to prove or disprove. Instead, we wanted to really analyze what communities were saying to us about this relationship. This is a little bit of the demographics of who attended these groups. In each of the 3 counties, we had quite long-term residents attend all of the sessions with, at least 30 years residents in the counties, and the participants were average age of 50 and older, and they tended to be more female than male. And the main question that we asked in these sessions was what changes communities were seeing to their water quality and public health since the start of unconventional energy development. All right, and when we analyzed these hours and hours of recordings and those initial focus groups, we got about seven hours of recordings, which we spent last fall analyzing. My graduate student, Owen Harrington, and I, who really led the analysis work, we observed 6 key themes in terms of topics of interest to the communities. So the observed changes to the water, possible contaminants and pathways of contamination in the waterways, the associated health effects. And then we also asked communities, what changes they would like to see. So that takes us to these last 3 findings, recommendations for improvement, obstacles to knowledge, and then what information people were relying on to form their opinions on this relationship. So we don't have time this afternoon to go through all 6 of these, but please follow up with me later if you'd like to know more. I'm going to focus on findings 2 and 3 here before turning it over to Sue. All right, so what I'm going to show you are some summary slides like this, And the numbers represent the number of mentions of a topic rather than the number of people who said that topic. So when we asked people to tell us what contaminants were most concerning to them, by and large, across all three counties, radiation was the contaminant of highest concern to communities. And I know that the session before lunch probably delved into the potential linkages between radiation and water contamination related to UOGD. All right, and then the possible pathways. So, how might communities get exposed to radiation in waterways? The main pathway that people were concerned with was the wastewater disposal and storage, and that was across all three counties. People were telling us a lot of stories about how that water is being dumped into local waterways or possibly spilled. So that's what people were most concerned with: is how is this tremendous amount of wastewater being handled in the communities, and are they at increased risks of radiation exposure because of that wastewater management side of things. All right, and then the health effects. Probably no surprise, given everything that we're reading in the news, possible radiation exposure. People were concerned most about how that might increase their risks of cancer. And then also we were holding these focus groups at the time when Pitt and the Department of Health were doing their public health study to try to understand the health risks associated with UOGD in a broader swath of counties in southwestern Pennsylvania. And then, of course, the Ewing sarcoma cancer cases in Washington County, they were a topic in the news. So that likely influenced communities' concern about potential cancer risks. All right. And then here's a representative quote from our Greene County focus group that I think nicely captures what communities feel in terms of this relationship between unconventional energy development, water contamination, and public health. So in Bobtown, which is a community in Greene County, we have a lot of kids, unfortunately, who at different times have had cancer, childhood cancers, again, all very rare diseases and of different types. So they are saying, oh, you're one in a million, you're one in a million. But how many people can hit the Powerball on one particular street or in one tiny community that has a little over 300 houses? So this, I think, nicely captures a prevailing sentiment, we would call it, across the three counties of how communities living in close proximity to UOGD feel about this technology in their communities. All right, so just a takeaway from these focus groups, communities are most concerned about potential radiation exposure from UOGD wastewater management, and that might increase their risks of cancer. So that's the key takeaway that we communicated to our geoscience colleagues. And I'm going to turn it over to Sue now, who will walk you through their analysis. All right.
Great. Thank you, Jen. I just wanted to thank the League of Women Voters for inviting us to talk. And I'm really pleased to be in this project working with Jen because I'm learning from her all the time. I'm going to talk about I'm a geochemist, so sort of the geological side of, looking at contamination that's related to water. And in my career since 2011, I've been working on this topic, water quality near UOGD, so unconventional oil and gas development. And we use two kinds of methods of investigation. One is field work to figure out what happens on a case by case basis. And then the second is statistical analyses. And on the picture on the left is an actual spill site that occurred back in the early days. We didn't work on this one, but we worked on another one that had the same contaminant. And it takes, 3, sometimes 4 years to figure out what happens in one site. So in order to really say something that is broad brush over a whole area like the southwestern Pennsylvania or the state of Pennsylvania, we haven't been funded to do this kind of field work on this, sort of case by case basis. And if you go to the next slide, Jen, we've focused mostly on the geostatistical analyses. Can you go to the next slide, Jen? Oh, I'm sorry. Okay, so I have multiple monitors and you're not running my monitor. Okay. So anyway, we've been able to do this geospatially with a really large data set of groundwater. And I can tell you where these data come from and tell you more about it in the questions. Uh, over the whole state, you can see all the unconventional gas wells in blue, and then where we have a groundwater sample data that we're getting from the state, who are getting it from the companies. We have something like 29,000 groundwater samples. And then we can look at this on a geospatial basis so that we can see what's happening wider and focus in on different parts of the state. So next slide. So I work on this with my grad student, Sam Shaheen, who's shown here, and he knows, I think, some of the people perhaps in the audience. And he spent a lot of time looking at statewide, but then also looking at either at Southwest PA or at Northeastern PA, which I'll sometimes call SWEPA or NEPA. If you could, we're trying to understand, is the UOGD affecting groundwater and water wells, and if so, how? So if you can go to the next slide, Jen. So as you know, as gas is produced, water comes back up with the gas. This is water that has been down in the shale for millennia, but in the beginning, when the gas is first produced, it can also contain the frac fluids. But as a statewide average, you can see some different elements here that are in the water. And also there's organic compounds. So if you click forward, on Jen, if you click, I just have to look at the right monitor again. You'll see, first of all, the water is 7 times saltier than seawater. And the main components are sodium and chloride. That's the same as what's in salt that we drink. It is such a high concentration, we call it a brine. And then it has species that are also called salt species, barium, strontium, and bromide. And these are very distinctive for this brine, so we can use that sometimes to see evidence that these wastewaters have contaminated somewhere. There are also toxic elements in these waters, such as thallium and arsenic, but they're present at much lower concentrations. And then there's also, if you click the next one, Jen, radium, which is the main contributor of radioactivity. So if you click the next slide, what we started doing with these large data sets is also the same thing the public health people do. They look to see if there's a higher incidence of different health problems near a shale gas well or within a certain radius of a density of shale gas wells. So we do the same thing, but we look at this water quality data set that we have, where there's about 40 different species that have been analyzed over these 29,000 sites. And then we try to estimate whether certain elements are becoming more concentrated closer to a shale gas well, a UOG well, or when somebody's water well is within a certain kilometer of a density of shale gas wells. And we look for statistical significance, so whether the increase in concentration near the well is statistically defensible as a conclusion. So what we've found is that there are statistically significant increases in chloride, barium, and strontium closer to these UOG wells or within a certain density of wells. And we found this in various parts of the state. So next slide. So that then poses the question, why are there regional increases in salt concentration in the groundwater? And in particular for the audience here in SWEPA. So the next slide, please. So here's the 3 counties where we have a reasonable data set. And by the way, the state's always giving us more data and we are digitizing it. And I pay undergrads to put the data online so that we can make these kinds of graphs. And in this particular figure, the dots are showing you where we have water well data, and then also where there's these UOGD wells. And this regional increase that's very, very slight in chloride, barium, and strontium closer to shale gas wells, that's a regional increase that we see. But when we look at it by like kind of using this computational approach of taking a window and moving it across the data set and just asking, in this window, does the concentration increase close to the well pad, and does this window, does it increase, and sort of move that window across this map, we can then actually plot out where are the hot spots where it increases. And you can see the hot spots here in the darker colors. So this means that in these hot spots, there are salt increases in the groundwater closer to or within a higher density of UOGD wells. And I want to emphasize that, this map makes it look really bad. Black looks bad. But these are very, very small increases in these salt concentration as you get closer to these wells. And so the regional increase that we've identified for this whole area is probably simply explained by a few localized places. So it's not regionally that the salt increases closer to these UOGD wells. It's probably that we see a regional effect, but it's only probably in a couple localized spots. So next slide. So what causes the hotspots? That's the next thing that you want to know. Each of those we call a hotspot. Next slide. And what we think is that the amount of salt in a wastewater spill that's at least 250 gallons could explain the increases in barium we observe within 1 kilometer. So here on this map, you can see the data that we've been able to get from the literature and from the state. The squares show, the red squares, spills greater than 250 gallons, and triangle spills greater than 500 gallons. And it turns out that when we look at the average barium, it's 23% higher within a kilometer of one of these relatively large spills. And so that's suggesting to us that the reason there's hotspots is that there are spills that have caused some of these salt concentrations we can see. Next slide. So we can look at across the whole state, and this again, this is the average barium concentration versus, it's kind of a complicated plot, but I'm just showing you that the barium is slightly higher, closer to UOG wells, and strontium is slightly higher near UOG wells. And if you hit and go forward, Jen, when we look at whether the barium is higher closer to spills, you can actually see an even larger effect. And if you look at the strontium, you see an even larger effect. So yes, there's a factor that's related to just being near a UOG well, but the real effect seems to be if you're near a well where there has been a spill violation. So next slide. So we can do something else with these data. And again, a lot of this is statistical. We can actually calculate how much is the increase in concentration of barium or strontium as a function of the number of UOG wells within a 1 kilometer radius of someone's water well. And you can see that there's, you can read it here. It's about whatever it is, 2 micrograms per liter increase in barium and about 10 micrograms per liter in barium per well within a 1 kilometer radius. But if you look at the same calculation for spill violations, it's even higher per spill within a 1 kilometer radius. And actually, again, these are very, very small increases. But if you look at the ratio of the effect, the barium effect to the strontium effect, and if you hit the advanced, Jen, the ratio of the barium to strontium is the same as the ratio of barium to strontium in wastewater. So it doesn't, this barium to strontium increase that we're calculating here per UOG well within 1 kilometer radius of someone's water well, the ratio of barium to strontium looks like the ratio in wastewater, doesn't look like the ratio in groundwater. So again, this is evidence that it is spills of wastewater that we're worrying about here. Next slide. Well, it turns out that when we look at barium and strontium, not only versus just the density of UOG wells within a 1 kilometer radius, if we and look at the spills within a 1 kilometer radius, but if we also look at impoundments, and in particular, if we looked at impoundments that were eventually closed down by the state. So these were impoundments that were used early on in the shale gas development in southwestern PA. If we look at those, we see that the average barium is 34% higher within a kilometer of these state decided problematic impoundments. So this is an example, one picture here of the Jaeger impoundment, which is pretty well known. So next slide. So what we think is that there are regional salt increases across southwestern PA, but they're caused by localized spots that are related to spills on well pads or leakage from impoundments. And we can see that there's an effect if the well pad is at higher elevation from the water well, then there's more evidence that the salt increase is detectable with our study. And so this really is pointing towards what we know, which is that in general, groundwater flows more or less downhill. It's following the hydrostatic head, but more or less downhill. And there have been some hydrologic modeling completed by a group out of Yale, led by Soriano and Jim Sayers and others. And the figure on the right just shows some of their output where they've tried to calculate based on well pad position what water wells downstream or down towards the valley would be vulnerable. And when we compare some of our hotspots to their modeling, it looks like it makes sense from a groundwater flow point of view. Next slide. So the other point I wanted to make is that one of these chloride hotspots, so these are hotspots where chloride increases ever so slightly, close to ever so slightly as you increase the number of UOG wells within a 1 kilometer radius. One of the chloride hotspots overlaps with one of these problematic impoundments, which is the Carter impoundment. And that was an impoundment that early on residents complained of air and water contamination prior to that impoundment shutdown. So to us, all of this kind of makes sense that we are seeing something in our statistical data that matches up with what people were complaining about. So next slide. So why do we even care about salt concentration? If you go to the next slide. The salt concentrations are many, many times higher than the concentrations of the toxic elements. And it's very hard, as a matter of fact, sometimes to even measure the toxic element concentrations in the brines because of all the salt that's present. And generally, these toxic element concentrations are not detected in our groundwater data set. So we have 29,000 water sample analyses, but it's very rare that any of these toxic elements, some of which are shown here, are reported as being detectable. And even at the detection limit, the limit where an instrument would be able to detect them, some species can increase a health risk. So even if they're below detection, it's possible for some species like arsenic that there could still be health risk. But what I have in this table here is the ratio of each of these elements of concern to chloride. And this ratio, which I've then shown over here as X to Cl, X being one of these toxic elements, this ratio can be used with our information about the increases in chloride closer to a water well to scale and say what would the increases be for these toxic elements. So it's no different than, I was cooking last night and I halved the recipe because my husband and I don't eat as much as my family of 4 total. And so you keep all the ratios the same and just scale up. That's all we're doing. And so when we do this, we can calculate how much of these toxic elements should be present in some of these hotspots. And then the next slide. So if the chloride increases near UOG wells in these hotspots, what do we predict for the toxic elements? So if you go to the next slide, we take that XCl, which is the ratio in the average produced water or wastewater, and then this is the 3.6 is how much the concentration of chloride increases per UOG well within a kilometer. And when we do that for these 3 hotspots of chloride, we see that the calculated concentration of thallium in these hotspots exceeds the the EPA maximum contamination limit for thallium in 3 of the 5 hotspots, the 3 that are shown here. We can do that for some of the other toxic elements as well. So we do it with arsenic, beryllium, and cadmium. They exceed 75% of the EPA limit in at least one of the hotspots. So although the concentrations of chlorides that we're talking about here and barium and strontium that we're talking about here are low and are not of a health risk, at least in these hotspots, we think there could be some concern about some of the toxic elements if we're right that there has been some leakage of wastewaters into groundwaters in these hotspot areas. Next slide. Well, it is of interest that, as I think probably most people in the audience know, just this year there was this study completed by the University of Pittsburgh School of Public Health, which was funded by the Pennsylvania Department of Health. And they concluded that there were health effects. And in this larger paragraph down here, I just sort of reiterate some of the health risks that have been highlighted by this study. But up here at the top, I talk about there was one conclusion that infants within 1 mile of one or more UOG wells during production phase were 20 to 40 grams smaller at birth. So infants were smaller, their birth weight was lower. And it turns out that thallium ingestion, which was the toxic element that I mentioned that did look like it was increased above the MCL by calculation, it could be above by calculation in 3 of the hotspots. Thallium ingestion, thallium is a poison, it is associated with low birth weights. So this does not mean that we've come to proof that that's what's happening, but it is, of interest that if it's water that is creating some of these health effects, and if it's the UOGD that's going on that's creating these health effects, I would suggest that thallium or might be one of the targets to think about and to study more thoroughly. So next slide. So the conclusions from my part, the geospatial conclusions, are that wastewater mishandling is the likeliest pathway to increase salts in groundwater near UOGD. And that's interesting to us, at least partly because that's consistent with community current concerns. And while the salts themselves are not problematic, there are other species in these wastewaters that are, and I showed you one calculation that suggested that there may be some concern about species such as thallium. I didn't really talk about this, but we have compared northeastern Pennsylvania to southwestern Pennsylvania. And we see that differences in hydrology between the 2 regions make a difference. So it turns out that there's more relief in northeastern PA. The distance from ridges to the bottoms of valleys is larger. And so that changes and makes it so that in some ways it's harder to see the salt concentrations that we saw in SWEPA. And then the second difference between the 2 places is the just really large amount of legacy extraction that's happened in southwestern Pennsylvania. And both of those seem to be important in terms of differences between the 2 regions. Okay, go ahead, Jen.
Sorry, I just had a hard time unmuting myself. So yeah, I just wanted to wrap up with some conclusions on how we bring the 2 pieces together here. So bringing into conversation the focus groups and the geoscientific analysis, we see that there is some convergence between what communities were concerned with and what the geoscientific analysis found. And in particular, that concern over wastewater management as a pathway of potential contamination. But then there was divergence in terms of the contaminants of concern. The focus groups were primarily focused on radiation exposure, where, as Sue pointed out, the geoscientific analysis was focused on elevated salt concentrations in the water and how that might relate to mobilizing some more potentially hazardous species such as thallium. And what we want to do next to carry this work forward is to do some more direct water testing in those hotspot areas that Sue was pointing out, to further test our results, because the water sampling database that we have been working with is just a one point in time measurement. So this would be an effort to go back out into those, into a smaller, more focused geographic area to do follow-up testing to see if there's still evidence of contamination and, whether our geoscientific analysis, which was largely statistical based, is in fact accurate. All right. And so what we would like to end with before turning over to questions from the audience, this is just a map of some of the hotspot areas that we would like to do some follow-up water testing in. So this is a project that we're in the construction phase of, if you will, but this is some impoundment areas around Washington County where our analysis showed some evidence of being hotspots. So we would really like to get in and work with communities to go into households, to do some follow-up water testing, to see what the water profiles look like today. So if this is something that some of the groups in the audience might be able to help us with, we are all ears, and here is our contact information. If you're able to help us with that follow-up water sampling, and if you have any questions or feedback on the results that we've presented today. And with that, we're happy to turn it over for questions, and we thank you for inviting us.
Well, thank you. Thank you, Dr. Brantley and Dr. Baka. We'll start the questions from the room.
Question from the room here. Are the elevated levels of barium and strontium high enough to cause an effect on the, sorry, reading handwriting. Ecosystems? Thanks. Fish, invertebrates, those sorts of things.
Thank you for the question. No, I tried to emphasize this, but of course it's always kind of hard. But the salt concentrations are only very, very slightly elevated. These are really small increases, and they are not hazardous to humans, and they're not hazardous to ecosystems either. I mean, what you've heard about, if you have a spill at the surface and it goes into a stream, you're talking about a huge amount of salt right into a stream. That would make a difference. But what we're talking about here is very, very slight concentrations.
Have there been any studies that looked at associations with injected brines in the subsurface?
So, all right. So that's a pretty broad question. First of all, in Pennsylvania, we've only recently permitted injection wells, and so we haven't been injecting brines into the subsurface for as long here as we have in other states. And there's a much longer history of it in Texas and in Ohio. And in fact, a lot of the brines from Pennsylvania were trucked to Ohio for a long time, especially early on. And in terms of statistical studies like what I showed you, I'm not aware of any that have focused on, looking at a statistical effect around injection wells. There may be a study out there that I'm not aware of, but I'm not aware of any. But having said that, there are cases, and I think some of you probably have heard about them. There are cases that have been in the news lately where injection is causing a problem, and then brine has been coming up in other legacy wells and that sort of thing. In Ohio, this has happened, and it's been happening in Texas also. So, I mean, I'm pretty convinced that a really well-designed injection well into a good reservoir is a really pretty safe way to inject and get rid of brine. But the problem is that there's always some problematic cases, right? There's always a few that there's some kind of problem, and so there's some brine that could come back up. And it's really pretty rare. There's tens of thousands of these wells in the country. It's pretty rare, but it does happen. And, you know, that's, if you're near one of those wells where the problem happened, that's really important.
Yeah, maybe a follow-up question along that line. What would we expect the concentrations to be right at the moment of the spill based on what you found? It seems like you would be sampling some months after the spill occurred.
So in the Marcellus, in this basin up here, the brines are like 7 times seawater. Depending on where you go in the country to which basin, the brines can be much less salty than that. We have some of the saltiest brines here. If it fell right into a, you know, if it leaked right into a stream, it'd be very easy to see it, but it would quickly wash out of the stream because of all the rain that we get, as long as the spill was stopped. So I've spent, you know, years now looking for data to show evidence of spills in streams, and of publicly accessible data. It's hard to find publicly accessible data that shows spills in streams. And why is that? It's not because the spills aren't happening. Spills do happen, but they're either small, so they don't contaminate the stream for very long, or they're contained, so they don't contaminate the stream for very long, or they're washed out because of all the rain we have. So by the time someone has publicly accessible data, you know, they're no longer seeing the evidence for it. And, you know, presumably the DEP goes out and collects data, but we don't always get access to the data, you know, after some kind of event has occurred.
Another question that came online, where does the thallium originate from?
I think the thallium is coming out of the rocks. You know, arsenic is, these contaminants that come out of the rocks, we call them geogenic. So genic meaning, you know, where it comes from, and geo is rock. So arsenic is another one of these elements that comes out of the rocks. And, you know, one of the things we've been able to do with this data set is also look just in people's water wells. And there, you know, there is arsenic and there's lead in people's water wells that probably have nothing to do with these industry, that they're, you know, the lead is probably coming out of people's pipes, and the arsenic is coming out of the rock that the water is coming out of, and it's natural. And this is a concern, and this is something that is communicated to the homeowners. But you know, it's kind of interesting because contamination isn't always from industry. The rocks do it too.
Great, thank you. There's a follow-up question on the spill question. And I guess what about spills that happen during dry spells? What effect does that have on the groundwater and the ecosystem there?
Well, that's a good question. You know, typically first of all, they line the well pads now. They didn't do this in the beginning. And if there is a spill, they put those socks around it that everybody sees, you know, that are spill stoppers. And so hopefully, if the company's doing what it's supposed to be doing, and many of them at least are trying, then they contain this spill. And then they're going to dig up the soil to take the, you know, all the soil that got contaminated and take that out of there. But it is kind of an interesting question, because in other climates and in other places, there have been spills that, you know, have gotten into the soil and then may create problems for longer periods of time. And, you know, some of the biggest spills have been out in North Dakota in the Baka oil field. And we've had some very big spills here in Pennsylvania also, but I think the biggest one that I know about that's been studied recently is out in North Dakota. And I do think that the different climates make a difference, but the different states make a difference, because different states have different rules about what has to happen after the spill. And, you know, one of the other things that's different is different companies. You know, some companies do a great job and they don't have a lot of spills, and other companies don't do a great job and they have more spills. And some companies are really good at cleaning it up, and some companies are not as good. And there's so much variability around that, in some ways it's hard to make complete conclusions, definitive conclusions.
One more? Okay.
One more question from the room here. Even though the concentrations of some of the things you're finding are very small, is it feasible that some associated fugitive substances could in fact have significant effects even at small concentrations?
Well, the concentrations that I'd be worried about, the elements that I'd be worried about are the ones that I flagged here. So arsenic, cadmium, thallium, and I think, I think radium also could be in that list. We didn't make a conclusion about radium because we're not 100% sure what the radium to chloride ratio is. It kind of seems to be very variable around the state. But in the hotspots that we flagged, I would be interested in really going out there and looking to see if those toxic elements are present at concentrations that are worrisome. So not necessarily everywhere, but in those hotspots, I would be very interested because I think they could be a health risk. So I would want to know what they are. And that's why we're actually using some Penn State money to start doing these samples. And our biggest problem right now, as Jen alluded to, our biggest problem right now is getting people to invite us into their home to take the water samples so that we can analyze and then, test our data set and look and see what we're seeing or what, might be going on there.
Thank you. Thank you for being with us today, Dr. Brantley and Dr. Baka.